In this video, we'll go over the angle sum and difference identities and double angle and half angle identities for trigonometry on Math 1060. We'll go over these by showing some example problems of where we can use them and how to use them. To start, we'll do a double angle example. We are asked to simplify the expression cosine of 2x minus cosine squared x plus 1. To start, we will look at the 2x inside the cosine function. If we notice, the other function has a theta in terms of x, so we want to use our double angle identity to get rid of that 2x. Our double angle identity is cosine of 2x equals cosine squared x minus sine squared x. We substitute this back into our expression in place of cosine of 2x. We get cosine squared minus sine squared minus cosine squared plus 1. And here we have a cosine squared x minus cosine squared x. So those subtract to 0, leaving us with negative sine squared x plus 1. If we rearrange this, we get 1 minus sine squared x. Now, if we look at our basic Pythagorean identities, we can see that cosine squared plus sine squared equals 1. That's a very common identity that gets used a lot in this class. If we rearrange that identity in terms of cosine squared, we see that cosine squared x equals 1 minus sine squared x, and that's exactly what we had in our expression. Therefore, our expression simplifies down to cosine squared x. Next, we will do an angle difference example. Given the following information about angles A and B, determine the exact value of sine b minus a. Here's the information that we are given. This problem asks us for a difference of angles. So we are going to use our difference of angles equation, which is sine of a minus b equals sine of a times cosine of b minus cosine of a times sine of b. Our problem, however, asks us for sine of b minus a, not a minus b. This is the same as simply relabeling our angles, and so we can just switch which ones we plug in using our identity. So instead of sine of a cosine of b in the first term, we'll have sine of b cosine of a, and for the second term, instead of cosine of a times sine of b, we'll have cosine of b times sine of a. In this equation, we need cosine of a and cosine of b. We do not have those values yet, so that is what we will do next. Starting with angle A, looking at the bounds, we can see that it is within quadrant 2, between pi halves and pi, so quadrant 2 on the unit circle. And then if we draw out a triangle and plug our values in, sine is opposite over hypotenuse. I drew my triangle this direction, the same as the values in quadrant 2, but we can draw our triangle in any direction we want as long as we are aware of the positive and negative sine and cosine values between the different quadrants. Using our Pythagorean identity, we can solve for x. We find that x equals the square root of 33. From here, cosine is adjacent over hypotenuse, and so we have square root of 33 over 7. And cosine in quadrant 2 is always negative. So our cosine of A would be negative root 33 over 7. And then we will do the same process for angle B. Looking at the bounds, we can tell that this is in quadrant 4. Again, I drew my triangle in that direction and placed the known values on the sides that they go on, so the opposite and hypotenuse. Using the Pythagorean identity, we can solve for x again. For angle B, x is equal to the square root of 35. Plugging those values in for cosine, we see that adjacent over hypotenuse gives us square root of 35 over 6. Cosine is positive in quadrant 4, and so our cosine value will be positive. Now we will plug those values we just found back into our equation. Next, we will multiply those across to simplify down to 2 terms. Because these have the same denominators, we can combine like terms and make them all into one fraction, which is the square root of 33 minus 4 times the square root of 35, all over 42. And that is the exact expression that it asks us for of sine of b minus a. For our last problem, we will look at a half angle example. Given the following information about the angle b, determine the exact value of cosine b over 2. It's given to us that b is between 2 pi and 5 pi halves, and that sine of b is equal to 1/6. We are asked for the cosine of the half angle of b, so we'll use our half angle equation. Cosine x over 2 equals plus or minus the square root of 1 plus cosine of x all over 2. However, this equation asks us for cosine of x. We do not have that information yet, so we will start by finding that. If we look at the bounds of b, we can tell that b resides in quadrant 1. We can tell this by subtracting 2 pi from both bounds. Doing this gives us 0 less than b less than pi halves, which is quadrant 1. And using the Pythagorean identity, we can solve for x, which gives us x is the square root of 35. In quadrant 1, cosine is positive. And so when we plug this into our equation, we will have cosine of b is the square root of 35 over 6, adjacent over hypotenuse. When we plug that back into our half angle equation, we'll get cosine of b over 2 is equal to plus or minus the square root of 1 plus square root of 35 over 6 divided by 2. When we divide by 2, that is the same as multiplying by 1/2. So we will end up with this plus or minus the square root of 1/2 plus square root of 35 over 12. Next, to find if that will be a plus or a negative big square root, we will look at the angle of our half angle of b. The bounds of b are given to us, but we are asked for half of that angle. We can calculate these new bounds by dividing each term by 2. That gives us pi is less than b over 2 is less than 5 pi fourths. When we look at where that falls in the unit circle, we can see that that ends in quadrant 3. In quadrant 3, cosine is negative. Therefore, for our solution, we will have negative square root of 1/2 plus the square root of 35 over 12. Here are some references in different textbooks that talk more about trigonometric identities and how we can use ones like the sum and difference identities and half angle and double angle identities. If you have more questions, tutors in the Aggie Math Learning Center will be more than happy to help you.